Swayam Prabha. Digital India. Educated India.
We will just be repeating the quiz 2 exam problem and trying to do it using using a neural network as a surrogate model. So I'll just show you both these as just primarily a demo class. So remember, we were doing this problem yesterday. We had like a one-dimensional wall. As usual, of course, I mean, while I'm doing this, as usual, feel free to interrupt me and ask any questions if anything is unclear. So I'm just showing the slides that I had yesterday. So we had this one-dimensional wall, and there was a heat source. Heat generation was there, and we wish to figure out how much the heat generation was given some thermocouple data, and we assumed a quadratic temperature profile. Wrote the corresponding loss function, which included both the differential equation loss as well as the temperature loss. Okay, so J ODE plus J temperature. Okay. And then we tried to minimize this function. We saw that you can minimize it in one of two ways: the direct approach, which I didn't do, and gradient descent. Okay. So when we did that, and we ran a code yesterday, we got these values. We ran a gradient descent code, and so what we got was these four values for the coefficients. So I called them W0 prime, W1 prime, W2 prime, W3 prime, because these were corresponded to X prime. Okay. So this was the situation yesterday, and I asked you how we could shift from X prime to X. I want to know again if somebody has an answer for that. So I'll just repeat the question. We had T of X, which was W0 plus W1X, W2X square. And we also had T of X prime. Actually, we should call it T prime of X prime mathematically. So the question is, how, now that we have found out W0 prime, W1 prime, and W2 prime, how do we convert from W0 prime to W0, W1 prime to W1, etc.? I mean, this set of variables to this set of coefficients to this set of coefficients. So suggestions, does somebody have any suggestion?
Sir, here, like, we can replace X prime by X minus, like the normalization factor. And then we can solve it. Like in that case, the coefficient of X will be W1 and X square will be W2 and the constant will be W.
So one way to find what to do about this issue. So to convert, replace X prime by X prime equal to X minus, we had X1 by X2 minus X1, where X1 was minus 0.025 and X2 was plus 0.025. Okay, so we could plug that in here, find out what expression comes, and we could directly find out what W0, W1, W2 are. Okay, so that is one way. There are a few other ways which work out for the specific cases we have taken here. One thing I would recommend it is, in general, think about the case where this expression is complicated and this expression is also complicated. And you actually want other quantities. Like, our main interest is to find out these. What is QV and what are the fluxes on the walls. Okay. So these are the specific things we are interested in. So for example, how do we find out QV without necessarily finding out all the terms W0, W1, W2? How do I find out QV? Somebody have a suggestion? How do I find out QV? Which specific thing do I need in order to find out QV? So remember, our original differential equation is there. D square T dx square plus QV by K equal to 0. So this means QV by K should be equal to minus D square T dx square. Now imagine a situation where we don't have a polynomial case, but we actually have something like a neural network here and a neural network here. Okay. So even though we might not find out the coefficient, we can at least find out the second derivative. So how do I write this in terms of D square T d? So how do I write this in terms of D square T dx prime square? What is this?
Chain rule.
Yeah, so what will that give me? I will not do it in detail, but this will be D square T prime dx prime square multiplied by what?
x2 minus x1.
1 by x2 minus x1 whole square.
1 by x2 minus x1 the whole square. Okay. So you can do the calculus and just check this out. And what is D square T prime by dx prime square? That is minus 2 W2 prime, which we have found out. Okay. And this is 0.05 square. So if you calculate this, can somebody calculate this and tell me what you get? So based on the original data, this should come to approximately, okay, I'll leave the calculation to you. I think you might get 195 or something of that sort. This should come to approximately 200,000 watt per meter cube. Can you just check the numbers?
192.712.
Okay, 192. Actually, you get 192 or something. Okay, 192 kilowatt per meter cube. So the original data based on which I generated this is actually turns out to be 200 kilowatt per meter cube. Now I'm going to ask, how do I find out flux on the left wall? Can somebody give me a suggestion? Without actually finding out, you know, W0, W1, W2, using just W0 prime, W1 prime, W2 prime, W3 prime.
We know the value of dt by dx is equal to 1 by x2 minus x1 into dt by dx prime. And
so what we want flux on the left wall is given by k dt dx at which location?
At 0.
No, at x equal to minus 0.025. Okay, so this is same as k times dt prime dx prime multiplied by 1 by x2 minus x1, but this is now calculated at x prime equal to so x equal to minus 0.025 is the left end, and x prime there is what?
0.
There it is 0. Okay. So if you calculate this, this comes to k times, what will this term become? Dt prime dx prime. at x prime equal to 0. So dt prime dx prime equal to
W1 prime.
W1 prime.
W1 prime plus 2W2 prime x prime, but this term becomes 0 because we are calculating x prime equal to 0. So W1 prime divided by x2 minus x1. Okay. So this, can somebody calculate and tell me what it comes to? K is 50. 50 approximately 250, 250.
4824.6.
Approximately 4824.6 watt, and actually it turns out, based on the data that I generated, that it was supposed to be approximately 5000. So this is the way to find out QV as well as flux on the left wall, etc. Even if you don't transform it to the original domain, you can find out the relationship between this derivative and the original derivative, etc., and calculate it. You can also, as somebody pointed out, you can convert x prime by x, and convert. There are other ways, clever ways of doing it. For example, I could try and match t at x equal to minus 0.025 with t prime at x equal to 0, and that will give me W0. You can do some clever things to find these out. Anyway, that's irrelevant. Most importantly, you should be able to find out our quantities of interest. So for example, even if I put a neural network here and a neural network here, and I am not able to write down neat relationships, I can always do this. I can always do a second derivative of a neural network, just like I did using back propagation. I can always do a first derivative of a neural network, and I can find out the quantities of my interest. So this is what this is how we can proceed this problem. Any questions on this? So this is generally an encapsulation of what you can do with physics informed neural networks. I showed you using a simple example of a quadratic, but you can do this for any neural network also. Any questions, comments on this? Questions, doubts?
Sir?
Okay. Yeah, please go ahead.
QV is a weight or an output of the neural network?
Both. QV is both. So QV is not an output. QV is actually a weight. Well, we are treating it as an unknown. It's not either an input or an output to the neural network. The neural network itself only consists of the following. It consists of, in this case, I'm doing it as a quadratic. So my neural network effectively looks like this. X is an input. X square is an input. And T is an output. You can see QV also as an input going here, but right now my only expression was T is equal to W0 plus W1x plus W2x square. I did not keep any QV dependence on T, but in my loss function, QV occurred. Okay, so we have that setting somewhere. Where is it? Oh, I'm shifted here. Yeah, here you can see QV is sitting as W3. If you wish, you can give this also as input, but you will have to write down what that expression is here. Finally, it turns out the dependence between W2 and W3 or W2 and QV comes through this. Okay, so that condition is kind of implicitly satisfied here. Make sense?
Yes, sir. So but in a neural network, we found out QV by the differential equation, right? But differential equation is not accurate in our case, because that is the that we wish to minimize. But QV should be equal to the weight of the neural network now, equal to some constant time W3.
No. I don't get what you're saying.
So like we got QV equal to minus d2 t by dx square, but that is not accurate in our approximation.
So it is accurate, and even if it is not accurate, it doesn't matter. It's a reasonable estimate, but it turns out to be accurate because you see this del J del W3 is n times 2W2 plus W3, correct? At the minimum, I will drive this to 0.
Yes, sir.
Okay, so 2W2 will be minus W3.
Yes, sir.
Okay, true here also.
Okay. So like, but in a neural network, that won't be so.
Oh, it will work out. It will work out. It is close enough to my order of approximation. That's all I care about, right?
Okay. Yes. Yes.
Right.
Yes. Thank you, sir.
If you are bothered about that, you can also find out QV in a least square sense find out least square average of these 4 points or 8 points or wherever we are calculating them, then find out QV. You can do that too, right? Root mean square average also you can do. All of them will give you roughly the same. See, we have some error bar across all these values. All of these are within that error bar. Okay.
Yes.
Okay. If there are any other questions, please ask me. Otherwise, I will just go to the surrogate model problem.
So the flux from the left wall should be a negative value.
Just check the sign. I might have made a mistake. Flux from the left wall. No. On the right wall will be negative. Flux from the left wall should not be negative. Why should it be negative?
So the slab, internally the slab is generating heat. So on the left.
So you look at the slope. The temperature is going like this. Correct? The heat is being added on the left. That's why it's going up immediately on the left wall. Minus k dt dx.
September போட்டிருக்கான் டென்டேட்டிவா செப்டம்பர் போல டிசாக்லாம் பண்ணிட்டு இருக்கான் அப்படின்னு சொன்னா கேட்டது அக்செப்ட் பண்ணிட்டேன்.
Deepak, can you just
அதோட சாய்ஸ் அத ஒன்னு அக்செப்ட் பண்ணிட்டேன்.
Yeah, can you go ahead please? Who was asking the question?
Me, sir.
Subhash. I might have made a mistake in the sign, but I don't think so. Let me just think about it. By the end of the class, I'll get back to you. Okay.
Okay.
Yeah. So we'll come here to the neural network as a surrogate model. I'm going to repeat the example, the problem that you saw in your quiz. Okay. So the same problem, we have a rectangular fin. Actually, I'll give you a minute to just read the question once more. The change here is, instead of using the forward model from your analytical solution, we are going to use it from a neural network as an output of a neural network. Okay, so how we develop that neural network is the primary thing I want to communicate in this part. But please do read the question once. Yeah. Okay. So what we are saying here is this. I am just given this data. Okay. I know it's a fin. I know there is an adiabatic tip. But I don't know how to get a forward model. Okay. So obviously in this case, we know we are simulating the case or going to pretend that this is just like the case where we don't know the forward model, okay, but we have some data. Apart from this data, which is supposed to be the actual current data, we have some historical data. So the conditions that the historical data has to satisfy is all this historical data should be from maybe for fins of different lengths. L might be different, geometry might be different, but all of these have adiabatic tips. Okay, so somebody over time has collected all this data. I'll show you, I have created some synthetic data of this sort. So this synthetic data over time, which has been generated, or this historical data which has been generated over time, we are going to use this to create a surrogate forward model, because without a forward model we cannot do any inverse problem. Okay, so that much is certain. So we need to create some surrogate forward model, and then we can use that in our offline Bayesian method, okay, with no prior. So I'll just roughly, you would already remember it from the quiz, but just to set context, I'll just roughly recap what you need to do for this problem if you had a forward model. If you don't want to use a neural network, but if you have a forward model, just 1 second. So conventional the TA might have sent you the solution. If not, in the forward model. Okay, what we do is, this is the analytical or exact forward model. Once again, in our problem which I am doing right now, we do not have this. But if we have it, then you know the procedure. I'll just show you the procedure very, very quickly. I mean, you guys have done enough of this, so you don't need really thing. Just for a refresher before I shift to the neural network, because I want to show exactly where the neural network plugs into this process. So this is our experimental data, which is the data we are trying to infer for. And then what we do is, remember, we start guessing effectively. So we say that K is somewhere between 20 and 60. And in the offline Bayesian model, all I do is I take some 9 uniform samples, okay, from between 20 and 60. And then for each one of them, this phi sim comes from the forward model. That is what I am saying is, if this was the K, then what would be the temperatures? This is what requires the forward model. If I know the K, I can find out the temperatures. Here is the distribution. If this is the K, this would be the temperature. And then for each one of them, I calculate the error. Okay, I calculate the S for each one of them. And then you do all the usual thing with Bayesian. Okay, P equal to P1 is e power minus S by 2 sigma square, etc., etc. And somebody has to give you sigma. And based on that, you find out what the mean possible K is, that is given here. Essentially weighted average or the expectation of K. And then you find out where you have maximum PPDF, and that gives you the map estimate of the conductivity. So you can see these two are not very different. Okay. The key thing here is the forward model gets used at one place. And what is that place? For a given k, or for a given meaning guessed k, what is the temperature? Philosophically, this is very much like how we are doing neural networks also. Okay, for a given guess of k, what is the temperature distribution? And then that temperature distribution is used in the usual Bayesian process. Now, what we will do is we'll use neural network instead of forward model. Okay, that is all we are going to do. So when I say that use neural network as surrogate model for a Bayesian estimate, all we are going to do is, okay, I had a forward model. Now I'm going to throw away that forward model and somehow come up with a neural network model for the case of a fin with an adiabatic tip. Okay. If I can come up with that, wherever I use the forward model, I can instead use the neural network. Now, before I go ahead and show you how this is done, please remember that this becomes very powerful in case the forward model is computationally expensive. Okay, the forward model is computationally expensive. If I can find out a neural network that runs much faster, which can be done for all these cases of weather, it can be done for Navier-Stokes, all these cases. We are doing toy problems, so typically the forward model is actually cheaper than the neural network. In practice, the forward model will be more expensive than the neural network. Okay, so any questions on this, on where the neural network will plug in and what the utility of that could be if we can find out how to get the neural network? Okay, so this is the process we are going to follow. We do not know the physics model. So the first step is we will assume that through some physics knowledge of the problem, that phi, this function phi that I want to find out a forward model for, an approximation model for, is some function of x by L and ML. Okay. Why am I choosing these two? These are non-dimensional and this is also non-dimensional. So dimensional analysis or looking at the governing equation will give you this. Okay. How will it give me? Let me just show you. D square theta dx square minus m square theta equal to 0 is the governing equation. I am not using the full governing equation, but a non-dimensionalization will give me the same thing. Now, if I divide by theta at the base, this becomes d square phi minus m square phi. Now, if I multiply and divide by L, this will become d square phi dx star square minus m square L square phi. I am skipping a few steps just in the interest of time. X star is x by L. Okay. And why should we write it in this form? We write it in this form because this is non-dimensional and that's the most appropriate form in general to deal with any kind of equation. Okay. So we write that function phi is a function of x by L and ML. M is square root of HP by KA. That comes again from some amount of physics knowledge. Like I said, you cannot always fully eliminate physics. You have to use some amount of physics intelligently to figure out what is going to be the input and output of the problem. Next is now for lots of pairs of x by L and ML. Okay. So you say, okay, somebody did just one experiment and they had only one output from one thermocouple. When ML for the problem was 5 at an x by L of 0.5, I got this temperature. You just note it down. Somebody else did something else. Somebody else collected 5 data points. Somebody else collected 10. It doesn't matter. Collectively, we get a lot of points. I'll show you how I simulated this, but just please do remember the steps that we are following. Once we know that this is the model, we collect data. In general, it is better to normalize the data. Here our data is kind of naturally normalized, at least for x by L, it is naturally between 0 and 1. We are not going to go more than that. Okay. So the next is to fit a neural network, and for our neural network, please excuse the font. This is supposed to be x by L and this is supposed to be ML. So we have two inputs. The output, this should be phi, not theta. And we have some hidden layer. Okay. So input has 2 neurons, output has 1 neuron. In the middle, we can choose as many neurons as we want. As usual, we guess for the weights of the neural network and solve it via some optimization scheme. Now, once you have this, once you have trained it, you now have a forward model for your problem instead of the analytical model. And exactly at the place that I showed you, wherever we were using from K to the temperature, there we use the neural network. Okay, we put the neural network in there, find out find out phi. From that, you find out the temperature and then you go ahead. And you can use a Markov chain Monte Carlo in case we want an effectively online Bayesian. From each sample, we guess the next appropriate sample to guess, or we use an offline Bayesian. Okay. So what I want to show you is this whole process in action in a code. And while I am trying to bring that up, please let me know if you have any questions even in what I have covered so far.
Sir?
Yeah.
Sir, in this case, like we just know the governing equation, but we don't know how the solution is going to be.
We might not even know the governing equation. I am assuming here we do, but it's possible for you to do this even if you don't know the governing equation, as long as you know what the appropriate inputs and outputs of that problem are.
Yeah. So now in this case, suppose there is a problem where there is a variation of x by L whole square or x by L whole cube, something like that.
Yes.
Now, in what neural networks problems we had done at the beginning, we were explicitly stating that x squared to be individual neurons, right?
No, that's not a neural network. That is for linear regression. You just have to give x by L. See, for example, here we know the solution is cos h of x by L times ml, correct? You have a cosine h term, correct? That's the actual analytical solution.
Yes.
Right? And if I write the Taylor series, it's going to have terms of x by L square, x by L cube, everything is there.
Yes.
Yes, but I am only going to give x by L. Why am I allowed to give only x by L? Because my theorem says, the universal approximation theorem says, if you give sufficient neurons in the hidden layer, I can cover all these cases.
Okay.
Okay. So that is the purpose. So please remember this. This is an important point. There are some things called kernel methods which do this. Okay, you give me x by L. I will also add x by L square. I will also add x by. That is explicit, what we call in the machine learning literature as feature engineering. I tell you explicitly what are the terms which are contributing. In neural network, all I know is it is some function of x by L. It could have square, it could have cube, it could have sine, or whereas whether as long as I cover all polynomial terms, effectively all of them sit into any Taylor series expansion. Okay. So as long as I can cover any Taylor series expansion, I can cover any function. Correct? And there is a theorem that shows that I can cover any function. You just need to give me x by L. Now, to the question that you asked, kind of modifying it. Now, if x by L, if the dependence is x by L cube instead of x by L, and I put a neural network, this is one neural network. In another neural network, I give x by L cube itself as input, then the hidden layer will be simpler. It will require lesser neurons. Here it will require more neurons. You might ask, how do I know? We don't. That is precisely why we leave the weight of that computation on the neural network's head and we just calculate the weight. Okay. Make sense?
Yes, sir. Thank you.
Okay. So here this code, I hope all of you are able to see something called FIN synthesized data. Is everybody able to see that?
No, sir.
No? Now?
Yes.
Oops. Yeah, so everybody is seeing FIN synthesized data, right? Yeah, so what I have done here, and this is of course, I don't have experimental data, so I made up fake data. What I did was I chose some ML, values of M multiplied by L somewhere between 0.2 and 10, and the values of X by L between 0 and 1, and I put 10,000 points, okay? And I generated the actual analytical solution. You can add noise here also if you want. Okay. The analytical solution we know is ML times 1 minus. So you will say, why should I generate it this way? This is just for demonstration. Okay. Ideally, what we should be doing is we have some simulations. Many people do this. So they actually have a simulation without the exact solution, but with a CFD simulation or something. They generate this data for past data. That makes them a model. The advantage of the model there is the model is much faster than the CFD simulation. CFD simulation might take hours. Neural network will take seconds once you have trained it. Before that, you have to run it for hundreds of hours. Okay. But once it is trained in any actual case, it can work much faster. Anyway, the point here is I have generated data of this sort. X is my input data, and it contains of, it consists of two things, X by L and ML. And Y is the output data. Ideally, like I said, from some prior computation or from prior experiment, this data has come. I have simply run it and it generated some data. Okay. It's sitting somewhere. Now, the next thing that I should do.
One sec. Still on you.
This is.
Sorry, I'm having trouble with the connection. Please try again.
Okay. So what I'm going to do is, I'm going to create based on this data. There is this thing called the neural network toolbox. Everybody is able to see this neural network start on their screens.
Yes, sir.
Okay, please let me know if something is not visible. I mean, I might have to share my whole screen or something. I'm clicking on something called fitting app. Is everybody able to see some neural network structure and saying welcome to the neural network fitting app?
Yes, sir.
Yeah, okay. Okay. So what we are doing is we are trying to find out a network that's going to map this input to the output. All this is completely automated. So I am going to say my input was that data X that I stored. Now, one way of doing this is you have an Excel file. From the Excel file, you import this X. And from the Excel file, you also import the Y. That is another possibility. You can see this now. Inputs is a 2 cross 10,000 matrix. Okay. It has 10,000 samples of 2 elements. And output is 10,000 samples of 1 element. What are these 2 elements? X by L and ML. Okay. Go here. Now notice this. I didn't discuss too much of this, but now the context is there, so I will say. So you will see this training, validation, testing. Okay, so this is different from the way you have been doing even linear regression so far. So remember, I have given 10,000 samples. Okay. Out of these 10,000 samples, 7,000 samples will be all that will be used to determine all the W's. All the weights of the neural network are being found out using only 7,000 data points out of this 10,000 data points. So what are we going to do with the other 10,000 data points? 3,000 data points. Remember, we have all this learning rate, etc., etc. All that is determined by this thing called the validation set. Okay. So I had briefly mentioned something called hyperparameter optimization. Now we keep the training set different from the set of data in order to test what is the best set of parameters for this problem. Okay. So that's called the validation set. We won't get into it too much in detail. Anyway, it's not relevant for the exam. But please do remember this. Parameters are found out from training. Hyperparameters are found out from validation. Hyperparameters include, typically they should include how many neurons, how many layers, etc. That we are not doing in this example. But learning rate and other hyperparameters of the problem are found out using validation set. Finally, there is something called the testing set. Now, why is the testing set different from the training set? That's because just like in an exam, we will give you some exercise problems here. But in order for us to find out how well you have understood the material, if I give you the same problem, that is not a good test of how well you have understood. Okay. Now, suppose I keep the training set. Imagine I have 3 points like this, which are in a straight line, and I fit a line to it. Okay. Or I fit a quadratic to it. Okay. And then I say my performance is perfect. I have fit all these 3 points perfectly using a quadratic. That makes no sense unless I give you extra points and check how well was this fit representative of the data. So this is sometimes called holdout. We hold out some data in order to check somewhere randomly. We will sample between these 10,000 points, take out some 1,500 points, and then test on that. And when I report my performance of my model, I will report on this because this one I anyway optimized on. I already made it perfect for the training set. Like I said, it's just like an exam. I can always give you example problems, and if I have trained children on addition of 3 plus 5 and I ask them 3 plus 5 again, it's not meaningful. At the very least, the number has to be changed. So the training set is different from the validation set. This is for parameters. This is roughly speaking for hyperparameters, and this is for actually finding out performance. Okay. So for example, if I am doing training for cancer detection and I tell some labels that this person has cancer, this person doesn't. Obviously, the training set, if I again give back, it might do really well. But only on unseen data can we actually report performance. So since I already only have 10,000 points, I will hold back a few just for testing and reporting performance. Okay. Go to the next set. So number of hidden neurons, let me say I give 20 neurons. So you can see instead of gradient descent, it has Liebenberg-Marquardt. It has scaled Kojak gradient, Bayesian regularization, etc., etc. I will just train using Liebenberg-Marquardt. It will report some number of iterations here, just like we did for gradient descent. That's what is called epoch. So this mu, etc., etc. are hyperparameters for the problem. You remember the lambda of the Liebenberg-Marquardt. What is the optimal lambda for the problem is part of the validation test set test. So it will find that out for the problem. Okay. And it is found out approximately 10 power minus. Okay. Now, if I plot regression, you'll see R square is 1. It has done really, really well. Okay, I gave it a lot of data points. It did really well. Suppose I went back. So just for fun, I'll change this to some 3 neurons. Okay, so we had 20 neurons. Let's just see how well it does. Let's train this. Okay, it has done it pretty fast. I want to plot the regression and see what it looks like. So you can see now, towards the end of the data set, even though our R is high, there is a lot of mismatch here. Okay. So that's why when we use a lesser number of neurons, the train is not so good. Okay, so after this, it is just a matter of saving the data, etc., which I have already done. What I want to show you is how I used it within the code, within the surrogate code. So what I have done here is the neural network that we fit with the 20 neurons, right? I mean, the case that I showed you, that I can save. MATLAB gives me an option of saving its weights, and then it functions just like a usual function. Then it works just like a usual function. Now, what I have done here is I have written a general inverse code using offline Bayesian. So I have given L, I have given H, I have given T, D, the area is T times D, perimeter is 2 times T plus D. Experimental data is exactly the same that we want for inference. Okay. And then I created a list of K. Okay. From 20 to 60 in steps of 5, we have those 9 points, correct? The standard deviation which was given in the problem was 0.008. Yes, I have called it E0, E1, E2 instead of P0, P1, P2 or P1, P2, P3 as was written here. This is our error. So what do? We go for each K within the list. Okay. And then find out for each X, we find out what is the appropriate temperature. So in order to make that prediction, remember that phi sim which we had, okay, or the theta simulated or the phi simulated. Now I can either use this, please see this would be the analytical solution. So the only place in this whole process where the neural network occurs, in this whole process of Bayesian estimation of K, is here in figuring out for a given X, what is the Y. Either use the neural network or use the analytical solution. If you have the analytical solution, use it. If you have the neural network, use it. So I just want to show you with the analytical solution. So this is the PPDF. Okay, using the analytical solution, you can see that the peak is around 50. Sorry about that. My Zoom is kind of troubling me. Yeah, you can find out what is K mean, for example. K means some 50.9392. Remember, this is using the analytical solution. I can also write down what the S was for the final S that we calculated. It's something like this. Now, suppose I switch and change this analytical solution to the neural network model. Okay, and run it. Let's see what happens. I don't know if it ran already or what happened. Okay, you'll see this is somewhat similar. Let's in fact check the value of K mean. 50.7129 versus 50.9392 then. Okay, I can also write down the value of S, 0.3149 and it was 0.3153, etc., etc. So you can see it is fairly close. Okay, so that is the advantage of a neural network. Now, this of course is in a case where we already know the analytical solution. But in cases where you don't know the analytical solution or the computation is expensive, you can actually do very well by having a neural network model instead of, or a surrogate model using a neural network instead of using the analytical solution. So that's really how you use neural networks in practice for inverse problems. So I am done with the machine learning portion of the course. So please feel free to ask me any questions that you have. Thanks, I am done. Professor Balaji will be summarizing the course tomorrow in class, and tomorrow's will be the final class of the course. So questions, comments, anything that you have? Any questions or doubts?
Sir, just a trivial question, like what's the theory behind how are we determining this hidden layer? Means, is it like multiple trial and like if I want to do
Yeah,
this
so that is
manually.
part of what is called hyperparameter optimization. You have to see what will work best. Currently, in the toolbox that I have, it has only one freedom. You can give only one layer and any number of neurons. Okay, but in general, in deep networks, you can use more than one layer. Sometimes by intuition, but overall, very broadly speaking, it is trial and error and experience with the specific type of problem you are working with. Okay.
Okay.
Sir,
Yeah, please.
sir, you used one tool, right? For neural networks, you used one tool.
Correct.
So how do you transfer the results? So whatever results you get, whatever parameters you get, how do you transfer to the code? It seems you're not.
So that thing is an option within MATLAB. It's available. It stores it as a structure. Okay, so if I show you, so at the end of that graphical tool, no, it has this option of saving the network. Oops. Now, if my network I saved as NN fit more data, that was the name of my network that I saved. Now, you will see if you go back here, it will have this number of inputs 1, number of layers 2, number of outputs 1, and there are all sorts of other parameters like input delay, etc. So connections, how is the bias connected, how is the input connected, how is the layer connected. Okay, now inputs, if I go here, okay, it has the weights stored there. Okay, so it is a structure within MATLAB which does all this. If you go to Python, things like TensorFlow, it has its own structure. So at the end of this process, there is a particular data structure for a neural network that for each, from each platform to platform or programming language to programming language or package to package, it will change. So MATLAB has its own version. The nice thing about MATLAB's version is that you can invoke it, you can call it as if you are calling any function. Okay, so the moment I called it NN fit more data, and if I come here and I call NN fit more data and I give it a vector with 2 inputs, it will just work just like a usual function.
Okay, sir. And you used Levenberg Markov algorithm, right?
And to train and find out the network weights, yes.
Yes, sir. So do we fix the parameter lambda, or does the
MATLAB finds it out by itself by experimenting on the validation set.
Okay, sir. So we don't have to do anything with the lambda.
Yeah. MATLAB is so MATLAB luckily has abstracted all that. So if you saw, its parameter was called mu. Okay, yes, if you play with it, see, all of you have access to this. I am going to send you the code. All 3 codes I will send you. Go to matlab.mathworks.com. Just play with that tool. It's called. You can invoke the tool by calling NN start. There are text ways of accessing it also, but this is easier for us. So if you put NN start, it will start the toolbox. If you play around with it, that validation set is precisely to find out what's the appropriate mu for this problem or lambda for this problem. Okay.
Okay, sir.
Yeah, it would have already experimented, it has found out, and then it will just go ahead with that. Okay. Anything else? Okay. If not, thank you very much.